In this video, I'm going to solve this related rate problem. So I have a hot air balloon. It's rising straight up from a level field. It's being tracked by a rangefinder, which is 500 feet from its liftoff point. And I'm given some information about the angle of elevation, and I'd like to figure out how fast the balloon is rising at the point where the angle of elevation is pi over 4. So the first thing I want to do is I want to think about what I'm given in this problem, assign some variables. So it makes a lot of sense to draw a picture in this case. So I've gone ahead and I've drawn the picture. So I've got a rangefinder. It is 500 feet from this liftoff point, and I've got a balloon rising from the liftoff point. Now, note that this is a fixed distance. It's always 500. It's not changing. That's an important thing to add to our problem. This is always 500 feet. Now, the other things in this problem are changing. Okay, so they need variables. Now let's see. So we're given that the angle of elevation of the rangefinder is increasing. We're given the rate at which it's increasing. Now, what is the angle of elevation? I've written the definition for you. It is the angle formed between the horizontal, so that's the horizontal, and the line of sight above the horizontal. In this case, it would be the line of sight, the thing that's tracking that hot air balloon. So it's the line of sight of the rangefinder. So that angle is here, and it is changing, so it needs to be assigned a variable. It's important in our problem. So let's assign it a variable. So we're going to let theta is going to be the angle of elevation. And now we're also given in this problem that the angle of elevation is increasing at a rate of 0.14 radians per minute. So d theta by dt is 0.14, or we might want to work with the fractional form later, and that's radians per minute. Now, I always like to think about my rates in the problem and whether they're increasing or decreasing, because that's going to determine whether it's positive or negative. In this situation, you can see that as the balloon rises, that angle is increasing, right? So it should be positive. Now, there's one other thing I should assign a variable, because I want to know how fast the balloon is rising. And that is going to be the rate of change of this distance here. So let's assign that a variable. So let's assign it x. And so x is going to be the distance between the liftoff point and the balloon. And so those are all the things that I need to assign variables, I think, and the things I've been given. So let's go to our next step, which is, let's think about what we want. All right, so I am asked how fast is the balloon rising when the angle of elevation is pi by 4. So that tells me I want the rate at which this distance is changing. So I want dx by dt at the specific instance when theta is pi by 4. Now remember, theta is a variable. It is changing, so we can't just go and plug in theta equals pi over 4 from the outset. We will do that at the end when we're thinking about that specific moment. Let's go to our next step. So the next thing we want to do is we want to relate our variables. Now we know we're dealing with an angle here. That tells us we likely want to use trig. So let's think about how we can relate our variables. So I've got my variables are theta and x. And if I think about it, I have the opposite side to theta and I have the adjacent side to theta. I do not have the hypotenuse. So I do not want to use cosine. I don't want to use sine. The best thing to use in this situation is tan, because then I get opposite over adjacent. Now you could use cotangent, but that might be not the best choice, because then you're going to have 500 over x, which isn't as nice to differentiate as x over 500. So let's relate. So we have tan theta is x over 500. So I've related my variables, theta and x. My next step, I'm going to differentiate. And remember, I'm differentiating implicitly with respect to time. The derivative of tan theta is secant squared theta. So I multiply by d theta by dt. On the right-hand side, I have 1 over 500 times x, so its derivative is 1 over 500 times dx by dt. Now at this point, I like to do the next step as, what do I need? And then I just do a little checklist. Okay, so I am given d theta by dt. I'm looking for dx by dt. So this is what I'm missing. I'm missing secant theta. And I think secant theta should be easy enough to get from our problem, because we're actually given that theta is pi over 4. Sometimes you might have to do a little bit more work to find secant theta, but in this instance, we're actually given that. So if theta is pi over 4, and we need secant theta when theta is pi over 4, well, secant of pi over 4 is the square root of 2. So I've now got secant theta, and now I have everything I need. So I can go ahead and I can substitute and solve. All right, so I've got secant squared theta, so that's going to be root 2 squared. I was given in the beginning of the problem that d theta by dt was 0.14. I prefer to work with the fractional form just because it's going to be easier for me to simplify. That's 14 over 100. And that's 1 over 500 times dx by dt. All I did there was I substituted into this equation. Now I'm solving for dx by dt. So I'm going to move actually things over to the other side of the equation. All right, so I've gone ahead and moved everything onto one side, and now I can cancel that. And I get 2 times 14 times 5, and that is 140. And that was feet per minute. If we check back, let's take a look back and see for sure that we got everything right and that we have what we were trying to find. So if I look back at the original problem, I was asked to find how fast the balloon is rising when the angle of elevation is pi over 4, and I was given the rate of change of the angle of elevation in radians per minute. So let's go ahead and just write a little closing sentence to close off this problem. So let's write the balloon is rising at 140 feet per minute.